In this video, we're going to talk about the discrete time Fourier series properties. These properties are used in a number of ways. One would be if we know a Fourier series for a function, we may be able to use these properties to use that Fourier series coefficient, convert it to the function we are looking for. The other benefit of this is we are able, by knowing the properties of x of n, we can make statements about Fourier series coefficients a of k without having to specifically calculate it, and vice versa. If you know certain properties of a of k, we can make some conjecture, some understanding of what the properties of x of n is. So by looking at one side in either the frequency domain or in the time domain, we can make comments or make observations about what the other side would look like. Let's go ahead and take a minute and walk briefly through here. First of all, we are doing Fourier series, which basically means that our signals are going to be periodic, and our fundamental frequency is going to be 2 pi over period n. And then the other important thing is that the Fourier series of these signals also going to be periodic, and the period is going to be exactly the same, so n. So as we go through these, we have the conjugate symmetry, which basically means that if my function, I shouldn't have drawn over this, so let's back up. And if my function is real, then my Fourier series coefficients would be of a of k would be conjugate of main minus a of k. So if you have never done a conjugate before, or you've forgotten what it is, all conjugate means is that if I have, let's say, a plus jb, that's my number. If I take a conjugate of that, all I do, I replace the j with minus j, so it'll be minus jb. That's all a conjugate is. So it's basically saying if my x of n is real, I can make an assumption that the a of k is equal to a of minus k. And then some of the other assumptions you can make here is that if you take a function and conjugate it, its a of k would also become minus a of k and gets conjugated as well. And then some of the other little more convoluted, I suppose this is a convolution. If you've got a situation where the two functions are convoluted with each other, when you go look at it on the other side, all you see is that a period multiplied by the Fourier series coefficient of the first function times the Fourier series coefficient of the second number. And then as far as the difference, if you have a difference between two functions, you can use 1 minus e to the jk omega 0 ak. And more generally, we can also do, this is called the first difference, but frequency shifting is always useful. Sometimes we want to take our signal and shift it in frequency in one direction or the other direction. In this particular case, we're shifting it by n omega 0. So a q by q, and that q basically would tell us the a of k for the new function would be a of k minus q. And then linearity allows us, so if linearity in the discrete time such that we have one function multiplied by another function multiplied by b, the same thing would happen to their coefficient when they go to the other side. Multiplication in discrete time will end up being more or less a convolution in discrete time. Okay. And then Parseval's relationship is, we don't use it in this discussion very much, but it's a very important idea. The idea basically is saying that the energy or the power in time in discrete time is going to be exactly the same as if you use the A of k to calculate it. And notice there's a 1 over n on the side of the discrete time, and that's missing because, as you know, the relationship between A of k and x of n, there's n multiplication in there. That's why it's on one side and not the other side. Some of the other properties we can look at say, okay, if x of n is real and even, by definition A of k is going to be real and even. And also, if it's x of n is real and odd, we can make assumption that A of k is pure, imaginary, and odd. And then there is the running sum, such a thing, and time reversal. And as you can see, time reversal, if x of minus n, then you just basically take the x of n's coefficient and just flip it around the y-axis, so A of k becomes A of minus k. Time scaling is available, and simply what it does is whatever the time scale is would be 1 over b A of k. So as you're time scaling, you're changing the frequency, and this allows you to change the frequency this way. Time shifting is another one, and simply all you have to do, if you're time shifting, you take e to the minus jk omega 0 and 0, which is whatever's your time shifting. And again, you can see a lot of similarities between this set of properties and the properties we talked about in the continuous time and its Fourier series coefficient. The one difference here is that the Fourier series coefficient is going to have this, is going to be periodic, has the same period as the signal, and it does not converge. So let's go ahead and take a example. This is just one way we can use this table. So I've written a little simple problem here for us to work on. It says find x of n that is real and it has a period of 6 with non-zero Fourier coefficients here. So one of the first things you do when you get a problem like this, your first property you have to consider is that A of k is periodic as the period is 6. So what they have done, right? They've given us some. So since it's real, we go to this table and say, okay, if x of n is real, then by definition, from the fact that it's real, we can draw the conclusion that A of k equals to A of minus k conjugated. Okay, and they say that the period is 6. That means our A of k is going to have a period. So if, let's say, if I decide for whatever case, I want to start at 0. You don't have to. Usually I actually like to mirror image it around the 0, because if they have equal, when we can use the Eulers to find sine and cosine. But for now, let's go ahead and start at 0. If I'm at 0, is there a A of k at 0 here? A couple of things we can so since this is real, since this function was real, A of k is equal to minus A of k. So that basically tells me that this means that I will have a A of 1 that is minus 5j. And I believe this is A of 0. So let's assume this is A of 0. If that's a of 0, it really doesn't tell us anything. We just have an A of 0. So they're not going to help us any. A of 2 says we have an A of minus 2 that is equal to minus 2. It's conjugate, but since there's no j, it's not a conjugate. So actually, let's backtrack. Since I already have A of 1 and minus 1, that means I know A of 0 is 5. I know A of 1 is minus 5j, so I should probably draw it the right way. Minus, so this is omega 0. We are in the omega space, and that is minus 5j, and we know that minus omega 0, a minus 1 is 5j, and then we also know that A of 2 is minus 2, which means 2, the second harmonic, because k is equal to 2, second harmonic is minus 2, and then the second harmonic in A minus 2 is minus 2 as well. So this will be minus 2. I've got 1, 2, 3, 4, 5. I need one more to make it complete, but there's, based on all the coefficients that are given to me, I can't find A3, and they said these are all the non-zeros are given as part of this. That basically means that the third harmonic, the value is going to be 0, and this is a period because 1, 2, 3, 4, 5, 6, and we know that I can start any place and end 6 steps later, and I got a full period. So that we use the properties, we use a lot of the information in the property to find this. So now if I want to write the x of n function for this one, all I have to do is remember I need the synthesis equation, and once I have the synthesis equation, I am done. So if you recall from earlier, we know that the synthesis equation for x of n is equal to the summation of k over a period, a of k e to the j k omega 0 n. Since period is 6, we know that omega 0 is actually going to be 2 pi over n, or another way of putting it is going to be pi over 3. So now all I have to do is expand this x of n over one period, and I'm good to go. So I'll start with minus 2 because that's the beginning of my period. This is k equal to minus 2, happen to have a magnitude of minus 2 too, but that's just a coincidence. So I will start with minus 2. This is when k is equal to minus 2. E to the, so omega is going to be pi over 3, so it's going to be minus j, and k for this one is going to be minus 2, so it's going to be 2 pi over 3, and then of course n has to stay here. And then we write the one for k equal to minus 1, which is going to be basically a of k for minus 1 is going to be 5j, and e to the minus j pi over 3n. And then continue on to next one is going to be k equal to 0. And if I do the k equal to 0, is the coefficient is 5. Since k is equal to 0, is going to be e to the power of 0 plus, I have two more terms to write because k equal to 3 is 0. So k equal to 1, it's going to be basically once again minus, not once again, but it's going to be minus 5j for a of 1, e to the j pi over 3n, plus or minus in this case because the k equal to 2 gives us a minus 2, so we do a minus 2 e to the plus j 2 pi over 3 plus, of course, the last one, the coefficient a of k is 0, so I'll put a 0 in front of it. So that's my x of n. I can get a little cleaner by just looking at this thing and say, look, this and this, if I apply the Euler's to them there, this one minus that one, which is going to be 2 sine of pi over 3n, if you recall. And then this 2 are going to be, because they're both the same sign, it's going to be more of a cosine here. Applying the Euler's, basically I'm applying the Euler. And this one is just going to be a 1. So if you want, it's not necessary to go any further at this point, but if you want to turn it to the sine or all that, this allows you to use the Euler's to get there. So as you can see, we were able to use some of the properties, first of all, to recognize just because they gave us these 3 coefficient, that's not all the coefficient that they've given us because of the fact that it's real. They already gave us the if I have a minus 1, I have a1 because it's just a conjugate at that. The same thing for a2. And then since it says the period was 6, I know that a of k is going to be periodic with period of 6. So we'll use that info. That's basically the reason we have the properties table, is to give us more information, allows us to better define the function, or in some cases, if I have the Fourier transform one function and I can use the properties table to convert it to another function, that would be great. We can use that as well. That brings us to the end of this presentation.